This is my lovely book, this book, and I recommend to everybody to take a look. It's fantastic book. And also there will be something about classification, group classification of ordinary differential equations, and it is given in this paper, the infinitesimal contact transformations in mechanics, published in 1889. And here this is collected works, the Zamata Anonymous. So this volume is 6 and published in 1927. And I wrote sometime a survey on group analysis of ordinary differential equations in Russian mathematical surveys, and it was published in 1992. And I used there a lot of these words. Now, here, just I repeat the same thing, but I don't need to spend time because it was already discussed twice. What the group is, and here what the infinitesimal transformation, generator, and he himself called it infinitesimal group, and the equations. But when I use it for students, they always make the same mistake. I never had any exclusions. This is just a rule. All students, you make one mistake. I never had anybody in my class that did not make this mistake. When I give the concrete example, they have this operator and then forget to put the x and y, not x or y. And can solve the equation or contain something wrong, which is not true. That's very good. So here is an example again with rotation, and it was discussed today. Again, admitted groups, it's also the same what we already had. This is a transformation. You can consider either as a transformation of points. You have a fixed frame, fixed coordinate frame, x and y, and then you change your x by means of this formula. Then your point x with coordinates x and y moves to the point with x bar y bar. But you can consider it as a change of variables. And this is very convenient, that's duality, because when you make extension of the group of prolongation to derivatives, you consider this formula like a change of variables. Then derivatives are changed like in the change of variables. Usual thing in analysis. Okay. And again, this example which I've already considered many times, and having this equation, you can find sometimes, what is the symbol? I don't know. It should not be that. It's a mystery there somehow. Maybe it's in the computer. It's just y prime without this one. You can find the symmetry without any infinitesimal calculations, determining equations, just to change the dilations with arbitrary parameter and find those coefficients from dilation which is invariant and obtain immediately the group of transformation with this generator. And this is just what happens after transformation. This is the transformation which you find in this generator, and if you make the transformation, your equation becomes like that, and this is equal to a constant factor which is not 0 multiplied by that. Therefore, if this is equal to 0, then left-hand side equals 0, and vice versa. This is 0, that side is 0. So that means that the equation is invariant. Not its form of the equation invariant, but the equation should be equal to 0. Now, the same definition for second order equations, just the equation is invariant if the same happens. What is wrong? Okay, that was the, okay. So it was mechanical. Thank you very much. one equation which is symmetry is non-trivial. Sometimes you cannot even just guess, it's not simple transformation. That's why group analysis is very powerful, and I call it a microscope of mathematical modeling. Why? Because in order to solve the model, you need a group, but a group of symmetries. In order to find symmetries, you should have some instrument, and group analysis is the instrument which opens, just reveals you the symmetry group. And like microscope, it was in biology in old times, you did not, it was clean water, but you look for the microscope, you see a lot of other alive creatures there, small ones. The same group analysis shows you that here is the symmetry which you don't see. So for example, if you have this equation, it's difficult to say what is the, of course, it does not depend on x. And therefore, it is invariant if you change x into x plus a parameter. So this is symmetry, this one. But also it doesn't contain, or it is, yes, you don't change y. But also you can find out that it has certain dilation. But plus, it is not easy to see. But still it is not that difficult. But this one is much more difficult to see. But solving the determining equation, which will be later on, you can find also this symmetry. And moreover, you can say these are all symmetries. So solving the determining equation, you find all symmetries. Again, when you say all, you should be a little careful, because nowadays people generalize the concept of symmetries, and then they always ask which symmetries. Yes, you can say point-wise symmetries. You can see the x, y as points, as coordinates of points, and this is a point-wise symmetry which was considered mostly by Lee. Then of course you consider also tangent transformation involving first derivatives, and that is already generalization, and today we have plenty of other generalizations. Because the problem with the practical works need that kind of generalizations. So, and these are generates, and those transformations are found. I found these operators by solving determining equations, integrate three equations and found these transformations. And those transformations by themselves can be useful in certain cases. For example, if you know one solution, you can act by those transformations, you will obtain again a solution by the fact that the symmetry is admitted by your equation. So that you can multiply the number of solutions using the finite transformation, group transformations. And already people discuss about prolongation formula, but I write them just with x, the same, without putting any sign of prolongation, because for me, each generator acts in the infinite dimensional space of variables, x, y, y prime, y double prime, and so on. But when we need to give an equation, we truncate that infinite scale. So anyhow, this is simple formulas for finding generalization to act, how it acts on y prime and y double prime, and they are obtained, this formula obtained just by formula of change of variables, change of derivatives under the change of variables, nothing else. And this is the determining equation. You act by your prolonged operator on your equation. So you put on the left hand side all terms of the equation, make it 0, and then act on that expression by that operator, prolonged operator, take them, eliminate y double prime, equation to f, then solve that equation, because it was shown by Kovalev today how to solve the determining equation by splitting the variables with respect to y prime. Different degrees. And then it was proved by Lee that if you have all solutions of the determining equation, then they form a Lie algebra. It's a linear space because the determining equations are linear. But this space has some more structure. It has a commutator. You can multiply the generates in a sense of generator, which was also calculated already by Reza yesterday. And it should be linear combination of the basis of operators, x. And just last thing what I will tell right now is equations with respect to their symmetries. How many symmetries can have with a single scalar second order ordinary differential equation? He showed that there are only the following possibilities. It can have no symmetries. Some of them don't have any symmetries, or one symmetry. Another is they can have one symmetry only, not even one generated X. It can have two symmetries. That you will say, okay, I can already count myself 1, 2, 3, 4, 5, 6, and so on. Of course, every child knows that, but not in group classification. It happens that for differential equation there are only the following possibilities: 0, no symmetries, 1, 2, 3, and 8. No equation with 4, 5, 6, and 7. If they have 4, they immediately have 8. Moreover, if an equation has 8 symmetries, maximum number, this equation is obtained by a change of value from simplest equation y double prime equals to 0. And then you can say, but why people study second order equations which are nonlinear and so on? Why just don't change it into y double prime equals to 0 and it's finished? We solve all equations. But unfortunately, the transformation of the second order equation admitting 8 symmetries requires the knowledge of at least one solution of the equation. So if you know the solution, then it's another to do. So that's it. And these are all possibilities you can find in my presentation. So I will not continue further because I will take time for another lecture. But let me just show a little bit. So 1, 2, 3 equation, and here we have the symmetries, and which is the form of the equation, the simplest form. And okay. And equation 4 is quite unusual. And this is a very famous equation. It was discussed even before me. And here you have this equation, but these are just representatives. It means that the equation admitting 3 operators can be either that form and so on, or this form. You can change it to that form by a change of variable. They are representatives of equations having 1, 2, 3, and 8 symmetries. So this is another representation, another equation having. No, we don't coincide. You cannot change the equation of this form to another form. And here, that equation, the simplest equation, which has 8 symmetries, all of them are written here. This is the so-called projective group. And now integration is another lecture. Integration using symmetries, second order equation using symmetries. So here I will stop after a small break. Let's make a small break of 5 minutes, and I will continue because it's second lecture. So